So, good evening, everyone. I hope you're well on this slightly wet and miserable Wednesday evening. This evening's annual history lecture is going to be presented by our speaker, who I will allow Professor John Tucker to introduce in a moment. For those of you that have found this link or come across this talk by some other means and you are not a British Computer Society member, welcome. We'll do a little introduction of the British Computer Society right at the end of the presentation for anyone that is interested in knowing a little bit more about us, as well as some links to our website, our upcoming events, and any other information that you might want to know about our branch and the Chartered Institute for IT. So without waiting any further, I'll introduce you to Professor John Tucker, who will introduce our speaker this evening. Thanks, John.
Thank you. Well, the South Wales branch of the British Computer Society has been a staunch supporter of the history and heritage of computing and organised computing history lectures each year for over a decade. And tonight it's a particular pleasure to invite a resident of South Wales, Troy, who has gained a lectureship at the Computer Science Department at Swansea University. Troy is a very versatile and knowledgeable computer scientist, educated at Newcastle, both for his undergraduate degree and his PhD. It's especially nice to note that his PhD actually was devoted to the technical history of early programming languages and the way in which they were described and developed. And in fact, it makes very, very interesting reading. And in fact, you can download it from the Newcastle Computer Science website. At Swansea University, Troy has shown an incredible versatility and enthusiasm for pretty much the whole program. And we're so pleased that he's able to also then lend some historical work for us at this annual lecture. So without further ado, I want to thank Troy and invite him to give his talk.
Thank you very much, John. I wasn't sure at all what kind of introduction I would be given here, so it's nice to have a little surprise to start things off. I've got a few of my relevant logos up here. This comes out of some research that I did in my postdoc primarily, although I'm still continuing to work on it. And well, guess which logos I didn't have a white version of and had to improvise. Okay, so I've been working with my collaborator at Newcastle, Cliff Jones, who was my PhD supervisor, since 2019 on this project on the history of concurrency. My PhD was on the history of formal semantics of programming languages. And towards the end of that, I said to Cliff, wouldn't it be nice to continue working together and let's tackle another area of theoretical computer science or formal aspects of computer science, let's say. I've learned since moving to Swansea that theoretical computer science means different things in different places. So we realized as we began working on this that it's a very, very large area. There's lots of work on concurrency. And so we ended up narrowing our scope a little bit in certain aspects. A very common thing to do with many research projects and something I tell all of my undergraduates that they will need to do during their third year projects. And so what we've been looking at is working towards writing a book about the challenges of concurrency from a historical perspective and outlining the various different methods that have been developed to address the design and verification, but particularly the design of concurrent programs. This involves some of the broader context and the emergence of concurrency outside of the formal aspects sphere, and also introduces as well something about the verification methods for sequential programs. But the bulk of the book is about concurrency. And it has this strong historical aspect as well as plenty of technical underpinning present as well. we have been working on this for a good few years now, and the book is in quite good shape. We're beginning to make overtures towards publishers at the moment, and hopefully will appear in the next, I don't know, maybe a couple of years. I'm not going to promise exactly. Now, within this project, my particular focus has been in two major areas. One of them, temporal logic, and I presented a talk on that at a conference called ICHST a couple of years ago, and I have a paper on that, which is going to appear in the proceedings once they eventually appear. And the other area is that I studied was about programming systems. So I looked at the way that programming emerged, and concurrency emerged and was handled in a programming setting, and then began to look at some of the ways that the programming of concurrent properties was managed. So that's what I'm going to be talking about here. And the title, From Monitors to Monitors, is of course cute, because who doesn't like a nice cute little title, and it's because it stretches from some early example of something that's called a monitor in a systems context, and then goes about as far as the monitors of Hoare. So we're talking about sort of the mid-1970s, and it goes on just a little bit after that as well. Right. When I first gave a version of this talk, it was far too long, but I've been given a very generous slot by John. So I have the opportunity to luxuriate a bit, I hope. I'll probably speak for somewhere between 45 minutes and an hour, and then we have the time for some discussions. A couple of caveats about what we don't cover in the book and what I'm not going to cover tonight. We haven't covered Petri nets. And we'll cover it in a little bit, but not in a great amount of detail, nor have we looked at concurrent separation logic, and that latter one primarily because it's a post-2000 development, and we limited ourselves to things that are pre-2000. Okay, that's a lot of scene setting. Let me begin to talk about how the problems of concurrency manifest in computing systems. And as I go through that, we will begin to get a sense of what it means to be concerned about concurrency in computing, as well as the various different ways that people attempted to address this. This follows a kind of a challenge and response model that is the shaping factor in the book on which we're working. Okay, so concurrency, which broadly speaking is about trying to get a computing system to do multiple things at the same time, emerges as a systems problem, driven especially by the fact that hardware speeds across different devices could be wildly different. So if we take some examples from an early paper written by Rochester in the mid-1950s, he wrote a paper tape reader, which was handling some of the input coming into this computing system. And by the way, when I say computing system, I'm talking about something that would probably have just been referred to as a computer at the time, but it's a collection of hardware components. In the mid-1950s, we're talking about bits of furniture, basically, that together are achieving some kind of computational goal when driven by a program. Okay, so a paper tape reader could take about 150 hours to read the input for something that the calculating unit would take 4.4 hours to process. A magnetic tape reader would be better and would significantly speed things up, but there's still a significant differential in the time there. If you imagine that the input reader is taking in values that are going to be processed, with that kind of factor of difference in the time taken to process them, you could have the calculating unit sitting idle for very long periods of time if it's simply waiting every time it needs to get a new piece of input. And that kind of thing is expensive. Then, as indeed now, people were concerned about the energy costs of computing systems. Then it was more about the financial aspects. Now, of course, we're concerned about the environmental costs of our large computing systems. And so it was seen as a benefit to try to utilize as much as possible of the calculating unit. By the way, I'm saying calculating unit in a very kind of general sense. Typically today we'd refer to a CPU, which is a sort of an abstract view of something that does some computation. So there were a couple of approaches to handling this, which you may have heard of. The polling approach, in which a processor periodically checks another piece of hardware to see if it's ready. But the problem with this is it still uses up quite a lot of time to do that request, and then it has to pause whatever else it might be trying to do at the same time to go and do that request. And the other strategy is the interrupt strategy, in which the slower piece of hardware notifies the processor in some way, which must handle this incoming interrupt. And this is a more complex thing to do, but it results in less dead time, less waiting time on the expensive hardware. And so this is the one that people tried to follow. What this means then, if we're following an interrupt model, is that we have a problem in which we have one processing unit trying to handle a few different things at the same time. It may be dealing with the I/O for a bit, and then once it has some data, do some calculations. Finished with those calculations, maybe it starts writing them somewhere else, maybe even switches to achieving another job. And then when it receives the interrupt, it has to be able to go back to where it was in the part of the program that handles the input-output. And this kind of switching between different contexts causes problems for programming. You have to make sure that you can get access to the working memory that you were using. You have to place yourself back into the same state you were in before when you were last on that particular part of the program. And once the interrupt has finished and you've done handling with the I/O, you have to go back to where you were in the other program. At the same time, there's another driver beginning towards the end of the 1950s, which is we have certain problems that actually take a lot of computation. And what we would like to be able to do is divide that up and speed it up. So typically things that involve matrix manipulations, where you have to do the same thing to all the elements in a matrix, usually can be split up across multiple different processes. And Dill in 1958 appears to have been one of the earliest people to identify that these two things, parallel programming, where you have one program and many processors, and time sharing, where you have one processor and many programs, are actually the same conceptual problem facing the same difficulties. And basically what those are interference and synchronization. Synchronization, making sure that you can handle when things are ready together at the same time, and interference, problems of separating out the space of the different processes. Okay. In the early 1960s then, Conway was working for the United States Air Force procurement. And at this point, there were methods beginning to be developed to handle this situation. And the most common one, as Gill explains, is to try to anticipate in advance how long a particular programming task is going to take, so that you can allocate a certain amount of time for the processor to be on that. And then once that time is over, you can then switch to something else. So you're dividing up your programming time into different chunks and trying to put the programs into those spaces. And this involves a lot of calculation beforehand. It also has significant potential for problems if you've got those calculations slightly wrong, and some bit of programming overrun its allotted time slice. So there was the desire for a better way to handle this. And in particular, to be able to write something so that it could be handled by a programmer who could specify exactly when switches needed to occur in the execution control of programs. Okay, so Conway's concern in the early 1960s was that too many people, particularly computing vendors, because he was working in procurement for the Air Force, remember, had conflated process and processor. It was known that you could have multiple processors within a program and that you could have multiple processors within a computing system. But the problem was that when people were providing, when vendors were providing solutions for the USAF's problems, he wrote, quote, when a proposal involved a multi-processor design, each processor was committed to a single process, end quote. This meant that there wasn't an effective method for being able to dynamically utilize whatever resources were available. So Conway worked on a system for storing the states of processes within memory of the computer system, so that suspension and resumption could be handled more smoothly. Additionally, he worked on adding machine instructions to the instruction set of the computers he was working with, called fork and join, where fork would split off a new process, and join would wait for any involved specified processes to be ready, unify their data together, and kill extraneous processes. Okay, and this was carefully handled together with his system for managing the memory and dividing up the state space. Conway does note, in addition to his 1963 paper, a footnote, in fact, which is usually an indicator that a reviewer or a referee have said, you know, you're not the only one that does this. So he did note that his approach wasn't entirely unique, but it seemed to be the one that achieved some kind of penetration that people picked up and actually used. This little diagram here is taken from Conway's 1963 paper, by the way. Okay, so who picked up and used this idea? Well, notably, it was used in a system for Project Genie. This was formed by Licklider for DARPA, the Defense Agent, oh, I've forgotten what it stands for. Defense Advanced Research Projects Agency, something like that. The US military's scientific research and development organization, basically. And this was based on a system that had been developed at MIT called Project Mac. That was that stood for Multiple Access Computer. And that was a system that was intended to allow multiple people to use the same computer at the same time. And this Project Genie was also to do the same thing. This was what was called time sharing, with the idea being that users of this system who had application programs were able to, no, I should phrase this another way. This timeshare system was able to handle multiple user programs at the same time by effectively utilizing the resources of the computer and switching between them as appropriate. The core operating system component that controlled the synchronization within this Project Genie was called a monitor, and it provided a few other services as well. It didn't just do synchronization between different programs. It did a few other things that you might find in a modern operating system kernel. But the monitor was so called because it monitored the different resources available of the system and allocated them dynamically across processes as appropriate. Okay, and it's worth noting at this point as well that the users, that is to say the people that wrote the application programs, didn't have any control at all over the synchronization that was going on. They had their sequential programs, and the system, the Project Genie system, just switched between them as appropriate. This system was bought by a commercial company called Timeshare, spelt with a Y, which was a commercial company, and they on their SDS 940, which was a modified version of the 930 computer, which was capable of doing some kind of slicing up of programs and data, was used as a kind of computing for hire. You could rent out time with this time sharing system by sending in your programs, and timeshare would manage the running of them and give you your results later. Okay. One reason that I particularly bring this up is because the process management system in Unix directly cited Project Genie and Timeshare as inspirations for the way that they handled processes. Now, this idea of having a centralized controlling system was kind of the common approach of the early 1960s, as presented by a survey paper written by Ted Codd. And those of you who know your computing history may recognize the name and associate it more firmly with databases. But Codd, who was working at IBM Data Systems Division in the early 1960s, presented a really nice early survey paper on multi-programming problems, an operating system that had programs which could run concurrently. It had shared variables, which is to say that you could have certain parts of memory accessible to any different program running within the operating system. It had some principles for ensuring non-interference between those parts of the data when needed, and block and unblock instructions that could be used for processes leaving and entering, no, other way around, entering and leaving, respectively, any interfering sections. It's worth pointing that out, and if you're curious and you're interested in concurrency, check out that paper. I think you might be surprised at just how many modern concurrency principles were already laid out by 1962. So underlying the control was a mutual exclusion mechanism that could arbitrate between threads. So if there were multiple programs or multiple parts of programs running at the same time, the decision about which of them got the opportunity to use the processor was handled by this mechanism, this monitor at the central part of the system. I think this probably has its first appearance in early work by Christopher Strachey in 1959, which was inspired by Project Mac. So some of the ideas in Project Mac, Strachey wrote up in a paper, and he had a part of his system called a director. So he had this little kind of metaphor of a director in an office, jealously guarding access to the precious resources of the computer, such as the memory. So it would divide up the memory and allocate it to different processes. It would decide which processes were allowed to use the calculating parts at any given time. And this kind of personification of the director as controlling is reflected in the role of the operating system at this time of kind of making all the decisions on the part of the programmer. Indeed, that's actually presented as an advantage by Strachey. Some kind of poorly formed or malicious program isn't able to interfere with others by overwriting their memory or something like that, because the director is in control. But some people were a bit unhappy with that. The idea of a centralized component, particularly if its workings are unknown to the programmer, makes it harder for people to actually exploit the benefits of concurrency and to get faster programs, for example, by dividing up the work or implementing their own miniature concurrent systems within a larger one. Given that many of the drivers for this was about efficiency, this monitoring aspect, whether it's called a director or a monitor, became the bottleneck for efficiency. If that wasn't running very well, then the whole system would slow right down. Moving on then to my next era, something I like to think of as the algorithmic age. From the 1960s, you could maybe see it start with the publication of the International Algebraic Language, IAL, in 1958, or the Algorithmic Language, ALGOL 60, in 1960. And it's sort of the beginning of a new era in computing as scientific and business computing begins to diverge. So we see Project Genie going towards a period of commercial success as a time-sharing service. We now see the algorithm emerging as the kind of the object of study around which computer science as a subject reified itself. I think this is something that's been pointed out by a number of historians of computer science. I think the situation is slightly more complex. It's not just about algorithms. And in some of my other work, I make the argument for formal semantics as a kind of an example of the earliest forms of computer science. But the algorithm as a way to represent more abstract view of computation, something that isn't tied to hardware, something that can be studied independently, is more portable, really caught on amongst academic computer scientists at this time. And the early 1960s is where we see the first appearance of the algorithms feature in the communications of the ACM. With this, algorithms for many different tasks began to populate CACM and other venues and be shared amongst various different people. The abstract nature of an algorithm, usually written in some kind of pseudocode resembling Algol 60, meant that it could be translated into whatever implementation language readers had available to them in their local institution or whatever. And so algorithms for concurrency began to appear as well. A very early one appears in a publication by Dijkstra in 1962 and is credited to Dekker in 1958. More of them appear later on in the 60s and especially into the 1970s. By treating concurrency at the algorithm level, it becomes something that users can think about. So in a sense, it's a popular word people like to use is democratizing, but I don't really like that. It's spread out, I guess. The individual programmer, the individual computer scientist is able to think about managing concurrency rather than it being embedded within an operating system and kind of controlled for them and out of their hands. It also turns out that algorithms are a very useful tool for expressing finer points of concurrency problems, and they remain pedagogically a very common tool for teaching concurrency and for exploring the problem as well. If you have a new framework in research, if you have a new framework for concurrency, you want to say, here's the kind of problem I can deal with it. And rather than showing it in a implementation accented program, let's do it in something a bit more abstract like an algorithm. Okay, so a little bit about Dekker's algorithm. He was working at Mathematisch Centrum. Oh, by the way, there's going to be a bit of Dutch over the next few slides, and my Dutch pronunciation is not great. I'm going to do my best, but apologies to any Dutch speakers here. So Dekker was working at Mathematisch Centrum in Amsterdam alongside Edgar Dijkstra, and it was Dijkstra who published the algorithm, although Dekker has written a retrospective himself. His name's Theodorus, I think. This has appeared in a recent volume called Tales of Electrologica, edited by Gerard Alberts. It's worth checking some of those out if you're interested in early computers. So what they were doing is they were trying to work out for the Electrologica machines that were being developed there in Amsterdam, how they could introduce these time-sharing things there. So Dekker's algorithm works for two processes, and I've sort of indicated on this flowchart kind of how it works. You have a flag for each section, which a process raises when it indicates it wants to try to get into its critical section, by which I mean a part of the algorithm in which it might work on some shared variables or do something that could interfere with the other process. If only one flag is, so it raises its flag and it checks to see whether the other process's flag is up. And if the other process's flag is down, it can go ahead. And if it's not, then it waits. Now, the problem is, what if they both have their flag up at the same time? Well, in that case, you have a turn taker, which alternates between 1 and 2, or 0 and 1, perhaps. to indicate which of the two processes has priority if they both want to enter their critical section at the same time. Now, this is the very kind of basic way of handling mutual exclusion, and the algorithm works pretty nicely for one process, or sorry, for two processes, but generalizes rather poorly to an arbitrary number of processes. Talking very briefly here about something that takes that same principle and works a lot better with an arbitrary number of processes is the bakery algorithm published by Leslie Lamport in 1974. So it avoids the problem of centralization that a lot of concurrency managing things have. And it uses this this metaphor, or this idea of the kind of ticket-taking machine that one would typically get in bakeries, apparently. I remember them at the delicatessen counters at Sainsbury's. That's where I first encountered these little machines. You know, you walk into the place, you take your ticket, and then whoever's number comes up first gets to go. And this is essentially how this algorithm works. But basically, every process has to do a lot of checking, and that involves quite a lot of what's called busy waiting. So when a process has to keep repeatedly checking to see whether it can go ahead, to see whether it has the lowest ticket, then that results in quite a lot of wasted time. So algorithms remain a topic of interest, especially because of the pedagogical reasons, as I've said, and for the illustration purposes. But a lot of them are marred with problems of complexity and synchronization across multiple processes and efficiency concerns, typically around busy waiting. What was desired then was a way to more effectively signal within an individual program how concurrency should be managed. And I use the word signal advisedly because now I want to talk about semaphores. Now, actually, Decker's algorithm was published by Dijkstra as a kind of a straw figure, I suppose. A way to say, yes, you could handle it like that, but actually, my approach is better. So this idea is a program level concurrency primitive, allowing a programmer to, whenever they want to do something with concurrency, indicate it as such, but without having to put the entirety of the synchronization algorithm with its large complexity within their program. And also with some simple program constructs, one could then reason about. And this could be at a higher level of abstraction than implementation. Dijkstra, his early research in particular was very characterized by a desire for generalization, in particular, in this case, moving away from the specificity of particular operating systems. And Edgar Daylight has written an interesting paper about this. So while he was working in the context of the Elektrologica X1, I'm not going to say that in Dutch, he was trying to produce something that could work on any kind of system. So Dijkstra was, for his PhD research, he had a physics undergraduate degree. He was working at Mathematisch Centrum, which I should say, by the way, is now known as CWI, Centrum voor Wiskunde en Informatica, I think. Still in Amsterdam. And Dijkstra's PhD was to create assembly language for the X1, and there he worked on the interrupt function. Shortly after finishing his PhD, or maybe just before finishing it, he moved to Eindhoven and worked on the Technische Hochschule Eindhoven operating system, THE as it was called. And that came a little bit later. So the inspiration for this program concurrency construct was called, it was first written about in Dutch, and he used the word seinpijlen, which means signal posts. So the idea is that they're inspired by railway systems that have those wooden posts with the little slats that go up and down in order to indicate whether trains can go or not. And maybe that's something that that is fallen out of use for long enough now that most people don't remember them. I don't think I've ever seen them personally in my life. Maybe some of the older members of the audience have seen them. But this was the idea, that you would have some kind of signal to control who could go at any given time. Essentially what this is a Boolean valued integer. That's how Dijkstra presents it. It could just be a Boolean, and there's also a generalized version which could be an arbitrary a natural number of arbitrary size. But the first presentation is this binary semaphore. It can be a 0 or a 1. The key is that there are two built-in operations, P and V, which you can use to manipulate them, and only those things can be used to manipulate them. Now, P and V have stood for various different things throughout history, including multiple different things in Dijkstra's presentations. Whether he's writing in Dutch or English, he refers to them as different things. So there is no one name that they stand for. In the paper I wrote on this, I go through a few of them. Another important point is that certain aspects of this have to be atomic. In other words, that the operation has to be achieved all at once. Now, atomicity in concurrency is a very important thing. It talks about, if we're thinking about the ability of a processing unit to switch between different processes, the atomicity or the granularity is kind of the smallest level of execution that each process can do before it has to switch, before another one can be switched. So these curly brackets here on the P operation indicate that everything between them has to happen all at once. You can't interrupt that and switch to another process in the middle. It has to all happen together. So P is about requesting access to some kind of resource. What it does is it checks the value of the semaphore, and if it is greater than or equal to 1, it can just be equal to if we're working with a binary thing, but if we have a general semaphore that can go up higher, then it could be greater than 1. And if that is the case, that indicates that the resource is available and it should be decremented. And then once that's been decremented, then the rest of the program can continue. Otherwise, if it isn't, then the process has to wait and then try again later. Okay. The V operation, and if you want a mnemonic for them, you can think of procure and vacate. The V operation is used once a process is finished doing something important, and it basically just says, okay, put up the flag, put up the post, put up the sign, the resource is now available. Now, this extends very easily to multiple processes by turning this into an integer value. And that also allows, that multiple resources by extending this to an integer value. And you can also wrap a shared integer variable within a standard binary semaphore to control who can access that at any given time. Now, this is a slightly higher level kind of construct than the operating systems I was talking about earlier, which means it needs to be implemented somehow. And Dijkstra worked on implementing semaphores for the X8 using an interrupt system, and later work would use hardware instructions such as test and set or compare and swap. And there are also a few other little points that need to be addressed if you're actually trying to implement these semaphores. How exactly do you handle the waiting process? If you're just repeatedly checking, then you've still got the busy waiting problem. A better solution would be to entirely sleep it and have the V operation wake up any sleeping processes. At that point, then you need to have some sophisticated method to choose between any number of processes waking up at the same time. Maybe you want some kind of queuing mechanism to involve priority, but this kind of thing isn't built into the basic semaphore. When Dijkstra presented this paper, this semaphore, in a particularly long paper justifying it, a 1968 paper called Communicating Sequential Processes, I believe it's called. I always get it slightly mixed up because CSP means something else as well, but I think that's what it is. Anyway, never mind. I don't think that's right. I'll come back to that, I'm sure. It'll be in my references. And he discusses something that he calls the deadly embrace, more commonly today called deadlock, where a situation where you have multiple processes all wanting to enter their critical section together that end up waiting for each other. Now, semaphores actually don't do anything to prevent that, and with lots of semaphores scattered around a large program, then the chance of concurrency bugs like that grows significantly, especially as programs were growing larger, as they were fast doing in the late 1960s, and also they were becoming more significant in terms of what they were actually controlling. This led a number of people, including Dijkstra himself, to begin to think about improving the structuring of programs. All right. So in the late 1960s and early 1970s, there was a hunt on for an improved concurrency structure that would take some of the benefits of semaphores, but address some of their shortcomings, such as the fact that poorly formed processes, including, for example, if you had multiple programs written by different people, some of whom might be less skilled programmers, a poorly formed process with a semaphore that never let go of a resource could just kind of hang on to that forever, or could introduce deadlock situations if it releases resources in the wrong order or something. So I'm going to look briefly at who was involved in this search for a succession to semaphores, consider why they were interested in it, and discuss what the result was. If you remember the title of my program, maybe you have an idea already what it might be. Now, I've noticed that something has appeared in the chat, but I usually don't look at the chat whilst I'm actually talking. I will rely on one of the chairs to interrupt me if it's something that requires my attention. Okay, so in particular, what we're interested in is a shared research effort from Edgar Dijkstra, Tony Hoare, who's in the left-hand picture there, and Per Brink-Hansen, who's in the right picture there. Hoare was working at the time at a computing company called Elliott Brothers, which came out of his interest in automatic translation, which at that point means translation between human languages done by a machine, during his national service, which had been in Russia. After working on systems programming at Elliott Brothers, he moved to Queen's University Belfast, where he got a chair at the end of the 1960s and began to settle into work on the theory of programming, because he was interested in trying to find ways to improve the correctness of programs. Brink-Hansen, who was from Denmark, had moved from electrical engineering to computing because he felt that computing was a sufficiently new field that he could make fundamental contributions to it. He was working at a computing place, a computing organization called Reine Centrale under Peter Nauer on various compiler and operating systems related projects. Now, if we notice, all three of these people came from serious systems programming backgrounds and took up the challenge of concurrency. Now, they were all working together on similar topics and met quite a lot of times. So trying to split credit for these ideas between them is difficult and probably not actually that useful. Brink-Hansen had to go in one of his memoirs, but Hoare wasn't particularly happy about the way that Brink-Hansen had shaped the story, I should say. The key points that are clear is that the three of them met at a summer school in Marktoberdorf in 1971, and then a follow-up seminar was hosted by Hoare in Belfast shortly afterwards, which Dijkstra actually didn't attend because he was worried about terrorist attacks. This was Northern Ireland in the early 1970s. What Hoare was interested in was working towards a theory of correctness for programming, and he recognized that concurrency created a lot of additional challenges, especially contention for resources. What his proposal is to wrap areas of contention in what he called critical regions, which would be specially marked in the program text to facilitate reasoning. And this would be with resource do computation. And then sometimes there would also be a condition on this as well, some kind of shared variable when B, some kind of Boolean thing. The process would be to, first of all, acquire mutual exclusion on the resource, test the shared condition if present, and then proceed to do the computation. And if that wasn't possible, to wait in some kind of pool. Now, you notice that I'm talking about acquiring mutual exclusion. In order to discuss this implementation idea, Hoare talked about using semaphores. So we have this idea of semaphores as a lower level primitive that are being used to build higher level primitives. Brink-Hansen examined this idea, and he thought that for problems that included a significant use of resources, these critical regions or conditional critical regions were simpler than using semaphores. And his contribution was to associate an event queue with every shared variable, so that processes, rather than waiting in a pool, could wait in some kind of queue, and that could have some sort of priority system, or it could just be first in, first out, to have a kind of a scheduling, so that processes were not waiting excessively long in order to be able to continue with their execution. A process releasing a resource would issue some kind of command which would make processes in the queue wake up and then try again. Dijkstra's contribution to this, which was presented in a paper called Hierarchical Ordering of Processes, I think. Should have written down the paper titles before I started this talk. Never mind, you can find them in the references at the end anyway. Had a rather 1970s approach to office roles as its metaphor, or its kind of shaping discussion. He talked about a secretary kind of guarding or gatekeeping a shared resource. And although he doesn't immediately say it has to be a female secretary, it's clear from the pronouns he uses that he's only ever considering the secretaries as being female. And directors have to call this secretary to request access. And if you want to guess at how he chooses to gender the directors, of course, they're all male. So if a director wants to try and get access, a director, which represents a process, wants to get access to a shared resource, gives the secretary a call on the phone and says, is this available? And if it's not, then the director goes to sleep and the secretary notes down the director's name. When the resource is freed by a director exiting, the secretary calls up the first director who requested the resource whilst it was unavailable and says, you can go ahead now. Now, if you remember back to the director system that I mentioned Strachey having, in that case, the director referred to the controller of the resource. Here, the director is a process, but Strachey's director differs here because it was entirely centralized. It was in control of the operating system. Whereas in this particular approach, the secretary is a routine that could be modified by the programmer. Okay, so it's interesting to consider why, given the similarity to the operating system approach, why Edgar Dijkstra chose to use that particular metaphor. Well, the 1960s and 70s is a particularly important time in the gendered history of computing, as it sees a transformation of computing labor as a feminized activity to a masculinized activity. Both Hicks and Ensmenger have written interestingly about this in their books. In this period, women are, before this time, women were the computer operators, but during this period, they were being removed from the kind of actual utility and use of the programs and the machines themselves, and are instead turning from kind of coal-faced programmers to pretty models posing next to computers in adverts. Ensmenger notes that beards were often seen as a mark of masculinity amongst a particular kind of programmer. We have a quick look, maybe. We see both Dijkstra and Hoare do have beards, but obviously Brink-Hansen is the less masculine of the three without having a beard. So whilst the authors Hicks and Ensmenger have written mostly about industrial programming and the kind of what you might think of as the working class of computers, I think it's interesting to note that Dijkstra, who's working in a kind of rarefied academic context, shows the same values at play as well. And as I'll discuss later, I think this is an interesting topic for further study. But let's talk a bit about the technical developments that occur after this. And finally, we arrive at our second instance of monitors. With ideas from Brink Hansen and Hoare and Dijkstra moving in a particular direction, the impetus is towards program code where the critical areas, the areas of potential contention, are clearly marked out by the programmer for better reasoning and better understanding of the program text as a kind of almost a literate object, rather than scattering semaphores around a program with transfers of control that might be seen as confusing. Programs instead could be composed of pieces from multiple sources a bit more easily. Now, this is in keeping with a kind of an almost aesthetic dogma in programming at the time, structured programming, which had a real emphasis on code readability and predictable control flow, as well as the encapsulation concept as presented by Liskov in particular. I saw her give a talk in 2021, actually at the same conference where I presented an early version of this, which was a nice synchronicity, where she described encapsulation as an idea as one of her proudest achievements. So the idea of encapsulation is that you put data together with the functionality required to access it. And in fact, you make it the only way that you can access those things. We see beginnings of that idea within the semaphores, but with the monitor concept, this is really brought to a greater degree, as well as encapsulating the synchronization mechanism. The actual shared resource itself is captured within the zone of control of the monitor. One other important inspiration for this work is the programming language Simula, in particular Simula 67, which brought together a number of these ideals of structured programming and was explicitly mentioned by Hoare as an inspiration. Note, by the way, that the book on structured programming, published in 1972, has as one of its authors Ole Johan Dahl, who was one of the creators of the programming language Simula. Okay, so all of these ideals led to Hoare's 1974 publication introducing monitors. The idea is to wrap a shared resource in a little package with all of the operations required to access it. The monitor can then be referred to from other places in programs and even externally. So this is the period of time where the idea of modular programming, that you will build a program out of little pieces of smaller program, I guess, can be, you can build it up by composing together fragments. So having this kind of control around the resource is a way to make the monitor handle all of the activities and resources associated with the shared. In my paper, I present a little bit more detail, and there's a bit more in the book as well about how you might implement this. But you can think of it a bit like, I learned programming in object-oriented style, so I think of it as a bit like a class where you have some kind of local attributes that are only accessible through certain methods. These methods include some kind of queuing. So queuing system is used for waiting processes, and there's a priority system built into these queues which hang on certain conditions. So I've kind of sketched out a little bit how this might look in this particular diagram here. So a monitor then provides all of the advantages of the conditional critical regions, with the conditions being present, but it groups together all of the related critical sections in one place. With semaphores and CCRs requiring processes to behave properly in their operations, monitors are now able to tolerate poorly formed processes simply by ignoring them. Now, the name of the monitor comes from the earlier operating system concept, as Brink-Hansen explained, but that was, rather than that one being sort of monolithic, one thing in the middle of the operating system that controls all of the synchronization. Instead, now the monitors can be in various different places around the program, not as scattered as much as semaphores, but nor as centralized as the monolithic operating system monitor. So there's a kind of a middle ground to be struck here, with the right amount of programmer control, with the body of a monitor being writable by them, but not so much that poorly formed processes can cause chaos throughout. And you might be thinking, well, surely it's a matter of taste. And indeed, different concurrency management systems in modern programming languages or in other kind of contexts tend to use various different places in this sort of centralized or decentralized control spectrum. So some questions still remained over proving the correctness of monitors, exactly how they could be used correctly to prevent as many deadlocks as possible, and also a tricky situation of nesting monitors. But there was an immediate positive response to the idea, and a few programming languages were written using monitors as their synchronization mechanism. Now, I'm going to pause just for a minute here and take stock as we hurtle towards the hour mark already. Having come from monitors and to monitors, what's next? Well, the three people that I've talked about kind of went off in different directions here. Whilst they all continued work involved concurrency in some respect or other, there were various different levels of abstraction there. So with Hoare continuing to work on the theory, he ended up developing a communication-based view of concurrency, leading to the process algebra strand of research, including some work by various Dutch computer scientists such as Klopp and Bergstra and Batten, and some contributions even by a certain John Tucker later too. Whilst theory remains, the theory of concurrency is a very rich vein of work, we cover some of it in our book, but not by all means absolutely all of it. It's interesting to note that there was some increased interest in 1970s with the real sort of heavy lifting of the foundational work on concurrency theory done in the 1980s. Dijkstra continued to be interested in kind of almost the aesthetics or the ideals of programming, as well as some work on programming constructs and correctness. And Brink-Hansen spent some time working on implementing things, particularly monitors, in programming languages and also within an operating system. So that's what I'm going to talk about in my last few minutes, is the programming languages strand. Okay, so in February 1972, Brink-Hansen had gone to Caltech, the California Institute of Technology, to give a talk on his ideas on queuing variables, and this impressed them enough that he was given a faculty position in the summer of that same year. The manager of the Laboratory for Information and Computer Science there, a man called McCann, cared more about using computers than developing them, according to Brink-Hansen, and so gave him the opportunity to do some development stuff, work on a new operating system, and take advantage of the department's new PDP 11/45. There's a couple of photographs that I've pilfered of some parts of that machine here. And what Brink-Hansen really wanted to do was to see whether his ideas about monitors could be used in the development of a high-level operating system, and in particular, whether he could write a systems programming language that used monitors. So the language Pascal, developed by Niklaus Wirth, had achieved a lot of success in systems programming, in compiler writing, And Brink-Hansen wanted to do the same thing for operating systems programming, essentially to reduce the programming effort compared to writing in machine language, which is what most operating systems had been written in at that point, whilst keeping as much of the efficiency as possible. So Brink-Hansen's interest in Simula gave him the insight that monitors could be used not just to encapsulate one instance of a data resource, but rather they could become a pattern for many instances with a kind of a class system. So he added processes, classes, and monitors to Pascal to get a language called Concurrent Pascal. And the goal with that was to get the compiler to do as much checking for synchronization bugs as possible. This involved having very subtle differences in the queuing mechanism compared to Hoare's monitors to reduce these possibilities and introduce the idea that one process could be running within one monitor at a single time. This idea may have come from Brink-Hansen to Hoare via Dahl, I think. This language that he built was quite simple. It had no recursion. It also had no garbage collection. And that meant that it was reasonably efficient, but not the most effective language for programming in. He wrote a series of operating systems, starting with a single user OS, and wrote a book about concurrent programming based on his experiences. He found it harder and more taxing than he'd expected, and the operating systems never quite lived up to his hopes. But what he had done is demonstrated that operating systems could be written in a high-level language with only a small recourse to machine language, and that only 4% of the operating system actually needed to be written in concurrent Pascal, the rest being written in a sequential subset. Okay, well, I've gone over the hour mark, and I think I now have 3 slides left. I think I'll maybe be another 5 or 10 minutes. I hope that's okay and people are still interested.
That's absolutely fine, Troy. No problem.
Okay, thank you. I have entirely minimized the video view at the moment, by the way, so you'll have to make some kind of noise if you want to get my attention. Right, so a little bit later in the 1970s, there was, interestingly, another development from Pascal that also used monitors. And this time it was done by Pascal's creator, Nicolaus Wirt. He was one of the firm believers in structured programming during the 1970s and felt that Pascal needed some development to be a slightly more useful programming languages. He was a bit worried that adding processes and concurrency would significantly increase the complexity of programs unless it was very carefully managed. And for Wirt, the key concept for managing this kind of complexity was the module, which he described as, quote, a set of procedures, data types, and variables where the programmer has precise control over the names that are imported from and exported to the environment, end quote. So he has this quite nice idea of a module as being like a kind of a fence which wraps up certain kinds of objects that don't quite fit with the nice structured programming principles. So he's thinking about assembly code to manage peripherals, for example, but also concurrent synchronization. And this is a kind of an acceptance that not everything in a big systems program can fit with the kind of nice abstraction principles that structured programming demands. So with the module as a fence around its objects, the programmer control would allow, there's a nice little quotation here, quote, precise determination of the fence's transparency, end quote. In other words, the kind of the encapsulation of the complex synchronization points could be used to keep those messy parts away from the rest of the program. Now, he mentions in some of his writing about this new language, which he called modular, being based on modules as a concept, that the module is a little bit like the concurrent Pascal class concept, but he doesn't properly cite Brink-Hansen. And by the time Wirt came to write a retrospective of modular and its follow-up languages, Brink-Hansen doesn't get mentioned at all. It's interesting to wonder why this might be. From speaking to some people, I remember this talk's being recorded, isn't it? I won't say exactly what people have said. Okay, so in Modular 2, which was a follow-up language in 1980, there's an interesting almost backward step. It might seem like a backward step, rather, because Wirt deliberately removed most of the concurrency apart from critical regions and signals in the sense of semaphore signals. But this was because Wirt had now become interested in real-time programming, less in big system programming, and had a new extreme concern for efficiency. So here we see a kind of a compromising on those principles of the abstraction and encapsulation, because in real-time programming, precise efficiency is what becomes required. Okay. So I'm going to talk about a final programming language now before moving on to some conclusions. This last one is a little bit more tenuously connected with the others, although Brink-Hansen's subsequent work after concurrent Pascal on what he called remote procedure calls was probably an inspiration for the tasking facilities of this language. The Ada programming language was initially created following US Air Force concerns about its software expenditure being very high. In 1972, they estimated spending about $1.5 billion per year on software. By comparison, the 1972 aircraft procurement cost was $3.5 billion. Okay, so they're spending almost half as much as they spend on aeroplanes as they on programs, and this is the US Air Force. So they were worried about the cost. But the idea that there should be one single programming language was put forward as a way to improve the system. If the US Air Force had some kind of requirement that everybody had to use programs of the same language, they could be shared more easily across the country, and the military as a whole, the US military as a whole, became interested in this and decided to make it a military-wide cross-service project. Now, interestingly, the name Ada was one of the very last things to finalize about the language. It was the latest deliverable in their project. It was decided over a year behind schedule. It was chosen after Countess Lovelace, as you might guess, and they actually consulted Lord Anthony Lytton, who was Ada's, at that time, closest surviving relative, who seemed a little bit confused about the purpose of the exactly about what a programming language is and what the purpose was. He referred to it in his letter as a radar language, but he was at least happy for her name to be used for this. One other slightly interesting thing to note about this is that there was some, whilst the process of creating the language was long and sort of very complicated, involving a lot of tendering and a lot of various different proposals. Some of them involved some formal definition work, including by Véronique Danson-Gouge and later by Dinas Björner and colleagues. It wasn't finished in time to contribute to the final language, but did lead to various modifications, including the catching of some bugs in some compilers. The design of the concurrency part, which was called the tasking system, was inspired by existing theory work on communicative methods, and it had this rendezvous concept. The idea was that shared environments would have the data or the shared resources inside them, and these particular environments would be owned by one particular task, and then it would say on what circumstances it would accept a rendezvous with another task. And that would enable other tasks to sort of come in when the owning task was ready, and then they could do some work together, and then the other task would leave. So in this case, it's not just the resource that's shared, it's kind of the entire running environment. With this, you can see there's a couple of entry points on this example here, and there could be a non-deterministic choice between available accept statements from this particular select thing. Accept statements would match against calling tasks and the body of the rendezvous itself. With it being, it could be implemented, they said, with either a shared variable approach with memory that's shared across multiple processes, or with message passing concurrency, this kind of new model of concurrency that Hoare and others had been working on, particularly Robin Milner also, and was clearly inspired by them both. Now, I'm going to move towards my conclusions now, but before I do, and I've talked a bit about the history of Ada here, let's have a little cautionary note taken by one of the people who worked heavily in the process of creating Ada. This is what he wrote in his History of Programming Languages paper. I'll quote, "The facts of history, the dates and names, have nothing to do with what was actually going on. There was a studied and logical progression, but the paper trail was constructed after the fact to please those who needed boxes filled." End quote. Okay, well, I think that is a bit of a cautionary tale. So I'll get to that. Let me talk some of my conclusions here. Monitors were the focus of this talk, which meant a few different things. The tricky middle ground between pure theory and a practical tool meant criticism from both directions. What would be the challenges in implementing them? How could they be verified correctly? Even as those who developed monitors moved away, Brink-Hansen, for example, remained very mixed on them. Similar constructs remain in a number of programming languages, notably object-oriented languages. Arguably, the utility of something like the monitor is quite pedagogical. The theory of concurrency might be viewed differently, and the implementation might be doing something quite else. But a monitor, I think, remains a useful way to think about how you structure synchronization, and it's still used to teach second-year computer science students at Newcastle, and I think also at Swansea. None of the things that I've mentioned here really kind of died or went away. Operating systems still manage concurrency. Algorithms are still taught. Semaphores are still a useful programming task, and so on. But concurrency, in other words, gets itself thrust in at various different levels of abstraction in computing. It's a challenging technical problem and needs to be managed whatever kind of layer of abstraction you're working at. Studying the ways that a technical problem emerges and is addressed in different contexts, I think, tells us something about the problem itself, but also about the process of science, with various levels of abstraction being created to try to address certain problems or facilitate reasoning or make certain things easier to specify or talk about, but also requiring different framing and shaping of the underlying concepts. That said, the historiographical examples here warn us against trying to find a fixed and neat story about history, looking at the kind of close collaboration between the trio in the early 70s shows us that following citations doesn't always work. And Dijkstra, for example, was notorious for never citing anything. In his book, A Discipline of Programming, there is a line, quote, "For the absence of a bibliography, I offer neither explanation nor apology," end quote. And the fact that there's a lack of reciprocal mention between concurrent Pascal and modular, when the two Weert and Brink-Hansen must have been very aware of each other, hints at the relationships between people without telling us much about the technology. And then the Ada quotation warns us, even from relying on archival documents, these might well have been recreated after the fact. And finally, what I'd like to say is my kind of takeaway from this, and something that has inspired me towards beginning to develop a new research project, is about looking at what I call illustrative devices. And maybe somebody else already has a name for this. Surely it must be a concept that's been studied in various other situations. But I'm talking about the metaphors, the analogies, the examples that are used to try to explain some kind of abstract concept. Like, for example, the secretaries that are put forward by Dijkstra. And he says he justifies his inclusion of this particular use by saying, we have chosen the example of secretaries and directors because, just like in real life, it is not clear who is the master and who is the slave. So to justify the choice of a misogynist explanatory device, he chooses a racist one. Great. So I think by examining these kinds of devices and how they're used within computer science, I think it can help us turn a critical eye on the way that social and cultural and contextual values get captured within something ostensibly very abstract. And that's something that I think is hopefully worthy of a few years of study, and I'm going to try and convince some funding body that it is. Right, I've been speaking for ages, so thank you very much for booking me the hour-and-a-half slot. Thank you for your attention, and I'm happy to discuss this further.
Right. Well, you've alluded, Troy, to one of the questions in your last remarks, because Thomas Reitmeyer said, what about these metaphors? He'd already got interested in the way the metaphors were beginning to pile up before we got to secretaries and directors. And his question was about whether or not the metaphors left the physical world of railways and semaphores and entered the world of, if you like, cognitive examples. So have you got any ideas of whether some sort of cognitive thing might have appeared in some of these operational modeling?
Yeah, absolutely. I mean, clearly, Thomas, we're great minds thinking in the same direction. I think there are definitely a lot of examples of this, especially in the early 1950s. There's a lot of talk of computers as giant brains and a lot of stuff about thought. And one thing that I think particularly worth remarking on in this context is the dining philosophers problem, which I haven't mentioned here in this particular talk, but I would like to study a lot more, where the idea very briefly is that you have some philosophers who are eating, and in order to get access to the food in the middle, they have to pick up 2 forks, but they can only pick up one at a time. And it's a problem that's designed to illustrate the situation of deadlock. But the very fact that they're mentioned as philosophers to justify them thinking, I think is so that they're being characterized, not just anthropomorphized, not just given agency, but these processes are being called specifically philosophers, kind of the pinnacle of thinking creatures, you might say. So I think this is a really interesting area of study, and I'm going to not fully answer your question by saying I agree that's fascinating and I want to study it a lot more. Maybe in a few years' time, if I get some funding, I'll be able to answer it more fully.
It's a nice point about the philosophers. I think that's the best you're going to get, Thomas. I got a question, which actually I was going to ask, but you kind of mentioned it at the end, because my first encounter with a very strong metaphor was Robin gave a talk and he used the master-slave metaphor. And I think that was an interesting. So my question to you is, when did the master-slave metaphor start to appear, at least in print? Do you have any idea?
Yeah, so there's a nice paper about this by somebody called Eglash, Ron Eglash, I think it is, from 2007. And it appears that the master-slave terminology first appears in the context of clocks. So it's in a horological engineering context, you might say, around the beginning of the 20th century, where you have one, like, I think it's in the context of like campuses or something, where you have one clock that's the master and then a series of other clocks slaved to that one central clock. Exactly where it then begins to appear in computer science is a little bit unclear, but it's particularly associated with hardware and with synchronization. And what I think is interesting as well is it's not really apposite. What we're talking about is something which signals and something else which waits for a signal, something that perhaps creates a direction and something else that follows that.
Well, it might have taken off because it gave somebody some kicks. You never know. Just like directors and secretaries, I don't know. The world is a very different place now, and one could talk about the change there. But interleaving and non-determinism, that hasn't somehow popped up with, you know, the time-sharing model and operating systems, because interleaving is so prominent in the algebraic theories that come later. At least people say that they are somehow connected to interleaving ideas. Is that something that would be different, or would it be implicit in some of the things that you've been describing tonight?
Yeah, so I think interleaving is interesting because you're quite right to say it crops up in a number of theoretical areas. For example, in temporal logic, they tend to say we will model concurrency using interleaving because you can treat the arbitrary non-deterministic switching between slices of different processes as though they were happening at the same time, because you could just choose arbitrarily small chunks of time for them to happen in. And I think that's an interesting example of something very practical influencing the theory there, that then they have to find a justification for it. They have to find a way to say, okay, it is actually sound for us to make that association. Because I think it comes very much from these early hardware systems where interleaving is what's going on. If you think about that paper tape reader and the central calculating unit, it is interleaving, going and doing some things with the input output, and then doing some work with memory, for example, on some other job even. So I think it's a similar kind of idea.
I noticed that Alan and Jens have both got questions in the chat. So Alan and Jens, would you like to ask your questions yourself? Here's Alan. Hello, Alan.
Yeah, loads of fascinating things to talk. I was particularly well. So this isn't the question thing. I'll come back to it, but just as a comment, I was. It says something about our ages, our mutual ages, and the slight anachronism when in a 1970s programming language, you commented on the fact that it didn't include garbage collection, which for anybody of a certain age like John will you will understand why that was a little amusing. But I was thinking about, it was really interesting that these issues are, but with very different paradigms. So although it's not true concurrency, coming back to that interleaving thing, if you look at, I mean, I was thinking particularly of JavaScript, because there, whenever you do UI things, you are forced to deal with these issues of things happening at the same time, and there's this sort of a little bit of a churn of paradigms, you know, from the sort of earlier event type thing, this use of promises, and it's about trying to make it easier. So yeah, I was interested in that, how it's progressing now, and what your and I mean, my feeling is driven by pragmatism, but thought about pragmatism, almost like going back to those early days of Dijkstra and that, when people were coming out, you know, it's almost like we've dropped, the academics have sort of dropped the ball a bit.
Well, I think there's an interesting kind of, like you say, almost cyclical changing of attitudes from very efficiency driven, very pragmatic, very practical considerations in early computing into the creation of a science of computing that's more abstract and based on mathematical principles. And then with the growing ubiquity of computing and the creation of especially things like embedded systems and IoT, with resource constraints, then kind of pushing programming practice, let's say, back into that same kind of efficiency first mode.
Yeah. I was going to say the Monad bit is straight from the sort of Glasgow functional programming, you know, functional programming for UI strand.
Sure, yeah.
And as far as I'm not sure though whether it is actually, you know, whether the link is there or whether it, but they call, you know, in JavaScript these monads that the developers talk about. So I assume that it's come directly from that. So yeah, so the theory can come into the practice a bit as well. Yeah.
Well, I find monads quite interesting. Is it? I don't know if I've ever said that out loud before. Is it monads? Monads, I don't know. Anyway, those things. I find them interesting because they are essentially that same kind of thing that Viet was talking about, I think. They're like a fence that you put around the bits of the world that are too messy to handle in your neat programming style. And you don't worry too much most of the time about exactly how it's doing that, unless you're very, very into the technicalities of it. But it's like there's this idea that there's parts of the world that are messy and you just have to find a way to deal with them, and whether you erect a module or a monad, you're doing something to hide it away.
Yeah. Great. Can I invite Jens to ask his question?
Yes, hello. Thank you, Troy. I wanted to pick your mind a little bit on something that grew, or at least I think grew out of the database community of software transactional memory, which also is dealing with concurrency issues and doesn't have the same sort of story that you present here with monitors and directors and things like that. So do you have any comment on that, or?
It isn't something that I've studied much, I'm afraid. I think it's something that Cliff is writing a little bit about for the book, but I think it's going in the chapter where we put all the things that we aren't discussing in great detail. I think that there is an interesting strand of work in databases and the handling of what they called, like, requests to databases so that they don't interfere with each other. And I think a lot of those are very similar challenges to concurrency, but it isn't something that I've looked at in a great amount of detail. Maybe it's something that I'll come to look at eventually.
Okay. Yep. Thank you.
Well, ladies and gentlemen, it's time now, because we've come to the 8:30 mark. And Andy, I think you want to say a few words before we shut up shop for the evening.
Yes, if I can. Thank you very much. I'm just going to put my camera on. There you go. I'd also like to try and share a slide if I can. It's just got some contact details for our branch. So hello again, thank you very much. We really appreciate you all joining us this evening. So thank you to all of you for watching the live stream. Huge thank you to Troy for their fabulous talk this evening. Very informative, really interesting. I could have done with you in one of my classes this morning. We were talking about the history of CPU, so that would have been very helpful. And to John, of course, for helping to organise the session for us today. For those of you who are new to our BCS webinars, I'm Andy Bellamy, and I'm the current chair of the South Wales branch. We are the Chartered Institute of IT, or for IT in the UK, better known as the British Computer Society, or BCS. We have over 70,000 members in over 150 countries worldwide, and we're a community of business leaders, educators, practitioners, policymakers, and we're all committed to our global mission of making IT good for society. Our South Wales branch has this monthly live webinar, like this evening. They're available to our members and non-members as either a live stream, and you can also watch it back on our BCS YouTube channel, which you can find through our website, through our branch website, as well as just doing a search for BCS on YouTube. Our webinars present on a diverse range of topics from across the industry, from fintech and health tech to cybersecurity, coding clubs, to our annual history and computing talk, such as the one you just watched. So just to wrap up, so if you'd like to know more about what our volunteer committee gets up to, maybe you'd like to get involved, maybe you're interested in becoming a BCS member, maybe you'd like to know a bit more about the benefits of becoming a member, or you just like to follow one of our socials to keep up to date with our upcoming events, then feel free to reach out to us through the links you should be able to see on the screen. And yeah, basically, thank you very much, everyone, for watching. Please do get in touch if you want to know more, and hopefully we'll see you at our next webinar. Good night. Thank you, Troy. And thank you, John. Thanks, everyone.